Rangana?
Yes, please.
Rangana, should you open your video?
Okay.
Just our faculty members say hi.
Yes.
So I am online.
Respected Principal, Dean Faculty of Sciences, Board of Studies Chairman Dr. Gangreddy, Head of Department of Chemistry L. Subramaniam Sharma sir, Chemistry faculty member, other department faculty members, research scholars, students. Welcome you all, my student PhD Viva voice presentation. So with this, I would like to introduce my student Anusha. She is going to present her PhD thesis. So please come.
Very good morning to everyone. I'm taking this opportunity to welcome my external expert, Professor K.V.S. Rangana sir from Benares Hindu University, and my research supervisor, Dr. P. Vascovardhan Reddy sir, and Dean Faculty of Science, Professor K. Krishna Reddy sir, and other faculty members, and all the audience who came to witness of my PhD Viva voice presentation. Coming to myself, I'm Anusha Gokanpalli. Today I'm going to defend my PhD. Today I'm going to defend my PhD dissertation entitled on Palladium, PEPPSI, and Heterocyclic carbene complexes catalyzed cross and Homo coupling reactions. Outline of thesis. Chapter 1. Role of various catalyst ligands and cross and Homo coupling reactions. Chapter 2 is study on the catalytic activity of palladium in heterocyclic carbene complexes for successive Suzuki, Mayura, and Bhopal-Hartwig combination coupling of 5-bromo-2-aminopyridine. And Chapter 3, Chapter 4, Chapter 5, and Chapter 6 are synthesis of palladium PEPPSI complexes and their catalytic application towards direct C2R relation of benzimidazole and C2R relation of benzoxazoles, and also applied for head coupling reaction and Homo coupling reactions. And Chapter 7 is summary and conclusion. Chapter 1. Role of various catalyst ligands and cross and Homo coupling reactions. Cross coupling reactions. Cross coupling reactions are most important and useful reactions in organic chemistry, organometallic chemistry to achieve CC and C hetero bond formation. This is the schematic representation for cross coupling reactions. This might be aryl halides or triplet, and this might be organoboranes or organotene and organogen, organosylyl compounds, and we get CC bond formation or C hetero bond formation. Tension metal, there are so many ligand metals are used for cross-coupling reactions, especially tension metal catalyzed cross-coupling reactions are more advantageous over other metals due to their less sensitive nature for oxidation, for being less toxic. Several cross-coupling reactions are classified based on type of nucleophile used in the reaction. For example, Suzuki-Maira, Buchwald-Hartwig, Sono-Cassida, and other cross-coupling reactions are there. Among all these coupling reactions, Suzuki-Buchwald-Head cross-coupling reactions are widely used. Suzuki-Maira cross-coupling reaction. Suzuki-Maira coupling reactions define as the coupling of aryl halides with boranes in the presence of palladium gas. It was first reported by Suzuki and Maira in 1970 by the reaction between alkyl or aryl boranes in the and aryl heteroaryl bromides in the presence of palladium tetrakis catalyst and base to give biaryls. This is the schematic representation for Suzuki-Maira cross-coupling reaction. This might be aryl halides or triplets, and these are the boronic acid and CC bond formation. Suzuki-Maira cross-coupling reactions are most frequently used method for the formation of carbon-carbon bond in pharmaceutical industry due to the availability of boronic acid and milder reaction conditions and less toxic in nature. Reported methods on Suzuki-Maira cross-coupling reactions. In 1999, Weinberg developed a method for Suzuki-Maira coupling reaction by using phosphine type of ligand at 110 degrees centigrade in long reaction time. These are some other literature reports on Suzuki-Maira coupling reaction. They use the ferrocene phosphine type of ligands, and they need a long reaction time. These are some other reports on Suzuki-Maira coupling reaction. These all the reactions require additional ligand, high temperature, and long reaction. Buchwald-Hartwig cross-coupling reaction. Coupling of aryl heteroaryl amines metal complexes that resulted in aryl heteroaryl substituted amines is known as Buchwald-Hartwig cross-coupling reaction. It was first reported by Mezita by the reaction between N-ethyl amino tributylene and several aryl halides using palladium chloride phosphate and obtain N-ethyl amino benzene derivatives. This is the schematic representation for Buchwald-Hartwig cross-coupling reaction. This might be aryl halides or triplets, and these are the amines. If you use primary amines, you can get secondary amines. If you use tertiary amine, you can get tertiary amine. Literature reports on Buchwald-Hartwig cross-coupling reaction. These are the reported literature. In Buchwald in 2001 developed a method for Buchwald-Hartwig coupling reaction by using the phosphine type of ligand in long reaction time. These all the reactions required temperature and additional ligand, high temperature, additional ligand, and long reaction time. Some other reports on Buchwald-Hartwig cross-coupling reaction. These are also required additional ligand and also high temperature, that is 135 degrees centigrade and 145 degrees centigrade, and long reaction time, that is 24 hours. Next is Mizrachi head cross-coupling reaction. Reactions involve the cross-coupling of unsaturated halides or triplets with alkene in the presence of palladium catalyst. Its base is known as head coupling reaction. Head coupling reaction become a necessary tool to bond olefinic group to aromatic ring. In the year 1970, Mazuroki and Heck explained the palladium catalyzed cross-coupling reaction of olefins with aryl halides. This is the schematic representation for Mazuroki Heck cross-coupling reaction. These are the aryl halides are triplets, and these are the olefins. You can get a substituted olefins in the presence of palladium catalyst. These are the reported methods on Heck coupling reactions. These all the reactions required additional ligand and some of the reactions required high temperature and long reaction time, and some of the reactions required additives. These are some of the reports on Heck coupling reactions. Direct CH arylation reaction. Tension metal catalyzed direct arylation of heteroaryl CH bond with RL hetero-RL emerged as an atom economical and attractive method. It is an alternative method to more established procedures such as Suzuki and Still-Nexi coupling reaction, because here we are replacing the pre-activation group with simple arenes, and we can get CC bond formation. These are the reported methods on CH correlation reactions. Here, Mayura and his workers have prepared C2RL benzazoles by using phosphine ligand and copper. But here, it required a high temperature and long reaction time. Sometimes long reaction time leads to formation of byproduct. And these are some other reports. They used JANPAS and triphenyl phosphine type of ligands for conversion of C2 the conversion of benzazoles to C2RL benzoxazoles. These are some other reports on CH correlation of benzazoles. Homo coupling reaction. Identical partners are involved in coupling reaction to form CC bond in the presence of tangent metal species to form Homo coupling product. Biaryl compounds are prepared by using Ullmann coupling reaction. It is the best reaction for preparation of biaryls, but functional starting materials are required. However, these functional materials are expensive and steps involved are tedious and limited substrate scope in specific to heterocyclic compounds. This is the schematic representation for Homo coupling reaction. Here, no need of pre-activation group. You can use simple azoles or some other aromatic arenes. Previous reports on Homo coupling reaction. Mori and his workers have developed a method for the preparation of bisazoles by using copper and triphenyl phosphine. Here they got lower yield, and also they required high temperature and long reaction time. These are some other U and TAN reported methods for Homo coupling reaction of azoles. They also used bimetals and also used ligands and high temperature and long reaction time. Limitations of reported cross-coupling reactions of Homo coupling and CH correlation reactions. Some of the reactions required additives, and some of the reactions required additional. Most of the reactions required additional ligands. Some of the reactions limited substrate scopes and low product yields. Harsh reaction condition need to high temperature. Few methods requires long reaction time. Introduction on N-heterocyclic carbenes. N-heterocyclic carbenes are electron-rich nucleophilic species in which divalented carbene is directly attached to at least one nitrogen atom. NHCs are either present in singlet or triplet state, depend on unshared of electrons, filling of unshared of electrons. In singlet state, unshared of electrons are paired and adopts sp2 hybridization with the diamagnetic property. In triplet state, unshared electrons are filled in different orbitals and adopts paramagnetic property. This is the stabilization diagram of NHC. Structure and general properties of NHCs. N-heterocyclic carbenes are electron-rich nucleophilic species. It depends on electronic properties of the electronic properties. Lone pair of electrons on nitrogen atom contributed to central carbene, which causes a 6-pi aromatic stabilization and increase the sigma electron density around the carbon. It will be decreased by back donation of electrons to another nitrogen atom. Due to their sigma electron donating property, NHC ligand from stronger bond with metal centers than most classical ligands. Compared to phosphine, NHC give tangent metal complexes that are generally resistant to decomposition and can thus be used as a pre-catalyst without excess of ligand. This is the NHC, and these two are this is the palladium NHC, and this is the phosphine palladium type of catalyst. Literature reports on the synthesis of metal-free NHCs. In 1916, Ainsley tried to prepare a stable and heterocyclic carbene by alpha elimination of chloroform, but he failed. He failed to isolate the carbene. Instead of carbene, he got dimer of NHC. After 3 decades later, Adiengo succeeded in the preparation of NHC by deprotonation. Here, Adiengo replace the simple phenyl rings with adamantines. So he get the carbene. These are the commercially available palladium NHCs, and this is the palladium PEPPSI complex. The cost of palladium NHCs are so high. Electronic effect on NHC ligand. Substituents and C4 and C5 position may not more impact on electronic properties of NHC, but the substituent variable N substituents, but variable N substituents would tune the electronic properties of metal NHCs. This is the steric impact of NHCs. But Nolan and Clever in 2010 developed have brought a concept of percentage buried volume, which suggests the fraction of volume of sphere center on metal that could be occupied with the NHC ligand, and also identified the correlation between percentage buried volume and experimental bond dissociation energy. Motivation of work. Catalysis through traditional catalyst is sometimes sensitive and require careful handling under inert atmosphere. A high loading of catalyst, elevated temperature, or long reaction time may often lead to byproduct. NHC-based catalysts are comparatively more nucleophilic than other catalysts and can effectively catalyze the CCC heteroband formation at shorter time. This may offer wide substrate scope for the development of variety of compounds. Objectives of my work: to study the catalytic activity towards cross-coupling reaction using conventional palladium catalyst and commercially available palladium NHC catalyst. To synthesize various novel, simple, explored benzimidazole bearing and heterocyclic carbenes and corresponding palladium NHC catalyst, that is palladium PEPPSI. PEPPSI means pyridine enhanced triplet catalyst preparation, stabilization, and initiation complexes. Next objective is optimization of palladium PEPPSI complexes towards cross-coupling and homocoupling of arylation, heteroarylation reaction to synthesize various bioactive N-heterocyclic compounds such as pyridine and substituent benzimidazoles, two aryl heteroaryl substituted benzoxazoles, bis-benzoazoles, and styrol pyridine derivatives. These compounds are characterized by characterization of prepared palladium NHC complexes as well as product by NMR, XPS, and SMEDOX, single crystal XRD, HRMS. Chapter 2 is study on the catalytic activity of palladium and heterocyclic carbene complexes for successive Suzuki-Maira and Buchwald-Hartwig combination coupling of 5-bromo to aminopyridine. Existing methods on Suzuki-Maira coupling reaction. Various protocols have reported for the synthesis of pyridine derivatives. In 2006, Buchwald and his workers have prepared pyridine derivatives by using phosphine ligand palladium acetate at 100 degrees centigrade in 8 to 24 hours. Later, Lenio and one of my senior have developed a method for Suzuki-Maira coupling reaction by using palladium PEPPSI Sone sp2 type of catalyst. Previous methods on Buchwald-Hartwig combination of bromopyridine. In 2006, Buchwald and his workers. These are the previous literature reports on Buchwald-Hartwig coupling reaction. These reactions required additional ligand, and some of the reactions required 120 degrees centigrade high temperature and long reaction time. Present work: optimization of reaction conditions for Suzuki-Maira coupling reaction. Here we are preparing a pyridine type of derivatives. For that, we have taken 2-amino-5-bromopyridine. This is the model reaction for optimization reaction. First, we started the reaction with palladium acetate without additional ligand, and we did not get any yield formation. Later, we have added ligands to catalyst, and we observed moderate yields. Later, we switched to palladium NHC catalyst, and we got the better yields when compared to catalyst plus ligand. Triphenyl tetra triphenyl phosphine palladium. Yeah. Triphenyl phosphine. Yes. Okay. Okay. Next, we optimize the bases and solvents. We have optimized the reaction with different type of bases: potassium carbonate and cesium carbonate and potassium tetrahydrobidoxide triethylamine and diisopropyl ethylamine. Among all these bases, the potassium carbonate gave the best results when compared to others. It gives the best results in ethanol water, that is 86% of yield. We got 86% of yield. These are the NHS palladium NHC complex, and these two are palladium PEPPSI complexes. Here we are comparing these two are available in our laboratory, and this I got this I have purchased this from online, and we compared all these palladium NHCs for Suzuki coupling reaction. These two are already reported catalysts. That's why we choose the single cycle TM. There are no reports on single cycle TM. That's why we choose single cycle. These three palladium NHCs are gave more or less same yields. Next is investigation of various palladium catalysts and ligands towards local Hartwig coupling reaction. In similar way, we have taken 2 amino 5 RL substituted pyridine was taken, and it was taken as a model reaction. We have started the reaction with palladium acetate and without addition of ligand, and we did not observe any yields. Next, we have added ligands to the catalyst and observed somewhat improvement in yield formation was observed. Next, we switch to palladium NHC catalyst. Next, state of reaction for Suzuki coupling reaction. We have tested the efficiency of catalyst with different catalyst loadings: 0.1, 0.3, 0.5, and 0.7, and 1.0. Among all these catalyst loads, 1.0 mole percent is insufficient for the formation of product. When you increase the mole percentage 1 to 1.3, there was no improvement in product formation. These are the synthesized C and N di-RL hetero-RL pyridine derivatives. These are most of these synthesized compounds are new, and also hetero substituted pyridine derivatives. This is the Proton Nmr Spectra of 5D compound. This NH proton is resonated at 6.63 and resonated at 6.63 has broad singlet, and this nitrogen attached to P proton is resonated at 8.62, and this nitrogen attached to C proton is resonated at 8.49 as singlet, and this nitrogen attached to carbon resonated at 8.29 as doublet because it has adjacent hydrogen. This is the 13C NMR spectrum of 5D compound. This is the HRMS spectra of 5D compound. This paper was published in Chemistry Selective in 2018. Chapter 3, synthesis of palladium and NHC complexes and their catalytic applications towards direct C2 arylation, heteroarylation of N-substituted benzene molecules. These are the existing methods for the preparation of C2 benzazoles. These are the reactions required additional ligand, high temperature, that is 160 degrees centigrade and 125 and 120, and long reaction time 48 hours. Present. When you see previous slides, the cost of palladium NHCs are so high. That's why we have prepared palladium PEPPSI complexes in my laboratory by using this synthetic route. These are the various palladium PEPPSI complexes, electron donating substituted benzyl substituted palladium PEPPSI complexes, and electron withdrawing type substituted benzyl substituted palladium PEPPSI complexes. We have prepared in my laboratory. Comparison studies between commercially available palladium PEPPSI and prepared palladium PEPPSI complexes. When you see the cost of commercially available palladium NHCs, that is 250 mg, is around 15,000. But in my case, it was just 9,400. And also, this is the steric map of catalyst palladium PEPPSI 3 catalyst. Here, by using this map, we have calculated percentage buried value for palladium IPR and palladium SIPR, and my catalyst palladium PEPPSI 3. Among all these three, my catalyst gave the high percentage buried value. Percentage buried value is directly proportional to the catalytic activity of This is the Xps Spectra of palladium PEPPSI 3. This shows these two peaks shows the binding energy at 338 and 343 that are related to palladium, and this is corresponding to chlorine at 196. This is the same EDAX spectroscopy. It shows the presence of palladium and chlorine in synthesized palladium PEPPSI complexes. Direct CH arylation of substituted benzene molecules with aryl halides catalyzed by palladium PEPPSI complexes. This is the we have taken benzene molecule and protected with benzyl type of bromides in the presence of sodium hydride, and next we have investigated prepared palladium PEPPSI complexes for C2 arylation of benzene molecules. Optimization of reaction condition. We have taken N-benzyl substituted benzene molecule and phenyl bromide as a model reaction. First, we started the reaction with palladium acetate and catalyst and triphenyl phosphate ligand, but at 70 degrees centigrade, we observed trace amount of C2 aryl substituted benzene molecule. Next, we switch to reaction with palladium PEPPSI catalyst, and we observe moderate yields, that is 76 yield percent of C2 aryl substitute. Okay. When we switch to palladium PEPPSI complexes, we observed moderate yields. Among all these palladium PEPPSI complexes, palladium PEPPSI 3 gave the best results because it has bulky NN triisopropyl benzyl bromide. No, because it need without base. Because it required base for nuclear. Yes. I have tried, but I did not observe any. Yes. 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 When you use boronic acid, in that case, there is no need of a base. I have checked. Yes. I have. Yes. Yes. Recyclability of catalyst. Recyclability of catalyst. We observed. I have recycled the palladium PEPPSI complexes up to unchecked for C-correlation reactions. We observed dropping yields. We have observed up to 6 cycles. After 6 cycles, bleaching of palladium catalyst was observed. That is why we did not get more yields. This is the Xps Spectra of freshly prepared palladium PEPPSI complexes and recovered palladium PEPPSI 3 complexes. Here we observed less intensity of palladium catalyst was observed in recovered palladium PEPPSI 3 complex. That is why we observed dropping of yields after 6th cycle, and it will be converted into nanoparticles. Palladium converted into nanoparticles. This is the same spectroscopy of freshly prepared palladium PEPPSI and recovered palladium PEPPSI 3 complex. Here, palladium and chlorine content weight percentage was 15 and 9, but in recovered palladium PEPPSI 3 complex, we have palladium and chlorine atom weight percentage is decreased. That is why we got less yields. These are the synthesized C2RL substrate benzimidazole. These are most of the reactions are new. Most of the synthesized compounds are new, and also some of the reactions with tried with heterocyclics. Assistant of effect of catalyst for in situ N-C2RL in single step. We tried the reaction. We tried to prepare C2RL benzimidazole in one step, but we did not observe desired product. We only got this product and substituted benzimidazole. Palladium PEPPSI 3 catalyzed direct C2RLation of NRL benzimidazole with RL hetero-RL halides. We tried to extend the substrate scope, so that is why we tried to prepare N-direct RL substituted benzimidazole. But we observed less yields when compared to NR alkyl substituted benzimidazole. Next, we tested the reaction with bromo-boronic substituted phenyl, and we got we want to know the efficiency of the catalyst for bromine and boronic acid. So we got we expected this product, but we got this one. Breaking of boronic acid also observed. Next is identification of possibility of isomers. We tried to extend the relation for 8D compound, but we did not get any expected product. We observed only Homo coupling of bromoanisole. This is the Proton Nmr Spectra of Palladium PEPPSI 3 complexes. These ortho-substituted methyl groups resonated at 1.12 as singlet, and these are para-substituted methyl protons are resonated at 1.31 as doublet. coupling constant is 5.6 Hz, and this CH ortho substrate CH proton is resonated at 3.44, and para substrate CH proton resonated at 3.00, and this methyl protons are resonated at 1.85 as singlet. This is the 13C NMR of palladium PEPPSI complex. This methyl ortho substrate methyl carbon are resonated at 24.22, and this para substrate methyl carbon resonated at, it is also resonated at 24.22, and this CH2 protons resonated at 48.73, and these methyl protons are resonated at 19.887. This is the Proton Nmr Spectra of one of the prepared compound. This methyl hydrogens are resonated at 3.8, and this CH2 protons resonated at 5.4 as singlet, and this is also singlet, and this and other remaining aromatic protons are resonated from 6.9 to 7.8. This is the 13C NMR spectrum of one of the prepared compound. This methoxy carbon is resonated at 55.38, and this CH2 proton is resonated at 48.40, and remaining other carbons are resonated from 110 to 160 ppm. This is the HRMS spectra of prepared compound. This paper was published in AOMC, Applied Organometallic Chemistry. Chapter 4, Investigation of Palladium PEPPSI catalyst coupling partners for direct C2 relation, hetero relation of benzoxazoles. Importance of relation of this is the present one. We have investigated the palladium PEPPSI complexes and coupling partners for C2 relation of benzoxazoles. Further, we have taken benzoxazole and aryl chloride as a model reaction for optimization. First, we started the reaction with palladium acetate and got ligand. We got trace amount of product. Next, we investigated prepared palladium PEPPSI complexes for C2 relation of benzoxazole with aryl chloride. Among all these, palladium PEPPSI 3 gave the best results because it has bulky triisopropyl group, electron donating triisopropyl group, and palladium PEPPSI 6 gave the lower yields when compared to other palladium PEPPSI complexes because it has electron withdrawing nitro group. Generally, aryl halides are homogeneous in nature, involving tedious workup procedures with the formation of byproducts impurities. Therefore, considering the environmental impact and through minimize the formation of the complex precipitates and increase the percentage optimization reactions are conducted with other coupling partners. Identification of the suitable coupling partners for C2 relation benzoxazole. We have investigated the palladium PEPPSI complexes for C2 relation of benzoxazole with aryl chloride. Next, we have changed the coupling partners with a different type of coupling partners and investigated the palladium PEPPSI 3. We have already investigated Palladium PEPPSI 3 is the best for among all other Palladium PEPPSI complexes. That is why we directly added to Palladium PEPPSI 3 complex, Palladium PEPPSI 3 catalyst, and the sodium tertiary butoxide is the best condition for the formation of C2RL substituted benzoxazole. When we change the coupling partner with benzoic acid, we got 48% of yield because breaking of benzoic acid required high temperature, and also due to some reasons we got less yields. And next we tried with diazonium tetrafluoroborate and sulfonyl chloride and boronic acid. Among these are also gave the less yields, but in case of boronic acid we got 95% of yields. In case of diazonium salts also we got 85%, but the cost of diazonium salts is high. It is expensive, that is why we avoided. Sulfonide chloride. SO2Cl. Sulfonide chloride. Benzene sulfonide. These are the prepared C2RL benzoxazoles. This is Proton Nmr Spectra of 3K compound. This all the aromatic carbons are resonated from 7.32 to 8.20. This is the 13C NMR spectrum of 3K compound. In this also, all the aromatic carbons are resonated from 110 to 159. This is the HRMS spectrum of 3K compound. The molecular weight of compound is 201, and 201 we got 201.9 M+1P. This was published in Applied Organometallic Chemistry. In chapter 5, Palladium PEPPSI NHC catalyzed head cup. These are the previous literature reports on head coupling reactions. These all the reactions required ionic. Some of the reactions required ionic liquids, that is TBAB, and also required high temperature, that is 130 and 140, and some of the reactions required a long reaction time. They are also used Palladium PEPPSI, but they required high temperature. Yes.
Whether you want this is the bond between nitrogen carbon and nitrogen or solvent structures are actually like that. Is there any difference between third bond and this next bond?
Imidazoliums.
So I will mix it.
Yes.
So I was saying in several cases, this is that. I got doubt that is different
Imidazoliums. That is not imidazolium. Yes. Yeah. Between nitrogen. Yes.
So it was mixed in several different.
Okay. I will check it. These are the reported methods on literature reports on head coupling reaction. Here we applied Palladium PEPPSI complexes for head coupling reaction. For that we have taken 2-vinyl pyridine and bromotoluene as a model reaction. First, we have started the reaction with Palladium PEPPSI 1, and we got lesser yields at RT temperature. When we increase the temperature to 80 degrees centigrade, we got 15% of yield. Among all these Palladium PEPPSI complexes, Palladium PEPPSI 3 gave the best results in water. It just gave 2.5 hours 95% of yield because it has a bulky trisopropyl group. Optimization reaction conditions for oxidative head coupling with aryl boronic acid. Previously, we have checked the reaction with the bromides. Here we are investigating the coupling partner with the boronic acid. Here no need of base, and here we are using air as an accident. And palladium PEPPSI 3 gave the best results when compared to others. These are the prepared olefin substrate olefin derivatives. This is the Proton Nmr spectrum of prepared compound. This olefinic hydrogen is resonated at this olefinic A hydrogen is resonated at 7.224 as doublet because it has adjacent proton, so it shows as doublet. And the coupling constant value is 16, so it shows the formation of trans. And this another olefinic hydrogen is resonated at 8.5 as doublet. Coupling constant value is 16. This is the 13C Nmr spectrum of prepared compound. This all the aromatic carbons are resonated from 122 to 122 to 155. Next chapter is dehydrogenated Homo coupling of N substituted 1,3 benzazole catalyzed by palladium PEPPSI complexes. Previous literature on Homo coupling reactions. Sai and Sardin have tried to prepare bisazoles by using additional some of the reactions required multi bimetals and some of the reactions required oxidant. But in case of palladium PEPPSI complexes, no need of oxidant. Here we are using air as an oxidant. The above reactions require oxidant, ligands, high temperature, and equimolar amount of copper catalyst. To understand this problem, it is necessary to develop mild and more practical reaction conditions towards the synthesis of biosols. We have prepared 9 palladium PEPPSI catalysts, and this catalyst highly effectively catalyzes the dehydrogenated Homo coupling of azoles using open air as a terminal oxidant. These are the optimization reactions for Homo coupling of N-benzyl substituted benzimidazole. Among all these palladium PEPPSI complexes, palladium PEPPSI 3 gave the best results when compared to others. It gave the best results in open air. Air as air using as an oxidant. These are the prepared bis benzazoles. These are most of the prepared bisazoles are new and most of these prepared compounds are new. Homo coupling reactions of benzimidazole with N electron with rank substituents. Benzimidazoles bearing N electron with rank substituents such as benzoyl and N-acetyl tertiary butyl oxycarbonyl derivatives were not proceed. Transition metal catalyzed by direct oxidative Homo coupling of azoles with electron deficient substituents at one position is reasonable yield have not been observed. This is the single crystal XRD of 2I compound. This is the evidence for the formation of bisazoles. This is the Proton Nmr spectrum of one of the prepared compound. This ortho-substituted methyl protons are resonated at 1.008 as doublet. Coupling constant value is 6.8. And para-substituted methyl protons are resonated at 1.3 as doublet. Coupling constant value is 6.8, and this CH proton para substituted CH proton is resonated at 2.9 as multiplet, and this ortho substituted CH proton is resonated at 3.5 as multiplet, and the CH2 proton was resonated at 6.24 as singlet. This is the 13th NMR spectrum of one of the prepared compound, and this ortho substituted methyl carbon is resonated. Ortho substituted and para substituted methyl carbon is resonated at 24.006, and this CH proton, this ortho substituted CH proton and CH carbon is resonated at 29.78, and this para substituted CH carbon is resonated at 34.30, and this CH2 carbon is resonated at 44.76, and this and remaining other aromatic carbons are resonated from 112 to 149. This is the proton NMR spectrum of one of the prepared compound. This is the 13th NMR spectrum of 2A compound. This is the HRMS spectrum, HRMS. Here the molecular weight of compound is 342. You got M plus 1P, that is 343. This paper was the manuscript under the revision in Chemosphere. Chapter 7 is summary and conclusion. Chapter 1 describe the comprehensive literature survey on various catalysts and ligands and cross-coupling and homo-coupling reaction. Chapter 2 is a new diversified, rapid and easily accessible and heterocyclic carbene-based Pallada-cycle, single cycle A1 exploit for the synthesis of C in diaryl heteroaryl pyridine allox from the less active parent 5-bromo-2 amino pyridine via sequential Suzuki-Buffel couplings. Surprisingly, both the coupling reactions proceed very smoothly, effectively in green solvent systems at faster rate with 1 mole% of catalyst. Chapter 3 is synthesis of a series of different symmetrical, unsymmetrical, and then diaralkyl benchimidazole bearing palladium PEPPSI complexes and applied their catalytic efficiency towards C2-aryl heteroarylation of N-substituted benchimidazoles with aryl heteroaryl bromides. Among all these prepared complexes, palladium PEPPSI 3 effectively tune the reaction at a relatively higher rate under milder reaction condition in ethanol water system. It avoids the use of ligand and additives. Chapter 4 is investigation of various different symmetrical and unsymmetrical palladium complexes and various coupling partners for direct C2-arylation of benzoxazole. Compare with the other coupling partners, boronic acid coupled with the benzoxazoles very effectively in the presence of bulky 1,3 bis NN246 triisopropyl benzoimidazole palladium PEPPSI complexes in open air. In chapter 5 is demonstrate an efficient and radius-free methodology for head coupling reaction, oxidant and oxidative head coupling reaction by using palladium PEPPSI complexes in water. It is best of our knowledge. This is the first report of palladium PEPPSI 3 catalyst for head coupling reaction under water under milder reaction condition without addition of surfactant ligands like TBAB. Chapter 6 is development of facial and efficient palladium PEPPSI catalyst that could successfully activate the CH bond between 1,3 benzoazoles via oxidative homocoupling reaction. Key factor in this methodology include low catalyst load, variety of substrate scope, even with sterically indebted substituents, that is triisopropyl, no necessity of any extraneous ligands and oxidant. Chapter 7 is summary and conclusion. These are the list of publications. These are the list of oral presentation. Final. I'm honored to express my deepest thanks to my research supervisor, Dr. P. Vasuvardhan Reddy sir, and also I would like to thank to Dean Faculty of Science, Krishna Reddy sir, and BOS Chairman Gangreddy sir, and my external expert members Ranganath sir, and all the department faculty members. Professor A.C. Damu sir, and Dr. L. Subramanian Sharma sir, head of the department, and Dr. K.S.V. Krishna Rao sir, and Dr. K. Venkatesh sir. And also, I would like to thank to CSR PUSA and DST Inspire for financial support. And also, I would like to thank, I'm extremely thankful to my parents and my brother and my husband. Thanks for your attention. Thank you. Right. Questions on thesis, sir.
Yeah, thank you for very nice presentation. I have few questions. Can I ask with the permission of
Yes, yes,
Mr.
you can. Yeah.
Yes. So why heterocyclic carbenes are required for the Suzuki cross coupling reaction or the Buchwald reaction? Because already triphenyl phosphine is very well known ligand, which can give the better yield. So what is the necessity of using the heterocyclic carbenes?
Triphenyl phosphine, if you use a triphenyl phosphine, they and also some of the reactions require high temperature. Triphenyl phosphines are decomposed at high temperature. And when compared with NHCs, triphenyl phosphines are less nucleophile when compared with NHCs.
So we can get the better yields, right? With
Yes,
the
sir.
triphenyl
Yes,
phosphines.
triphenyl phosphine are decomposed at high temperature.
At high temperatures.
Yes.
Okay. NHCs are recyclable or they are soluble?
They are solids.
Because in the chapter number 3, you
These
mentioned
are the soluble. These are the homogeneous catalysts.
means you can able
But
to
NHC,
recycle the catalyst
yes, sir.
because they are insoluble in your reaction medium.
No, sir. It is soluble in reaction medium.
Then how can you recycle it?
We have recovered by using column chromatography.
By using column chromatography.
Column
Okay.
chromatography.
Okay. So what is the nature of NHC ligand? Whether it is a neutral ligand or a acidic ligand or a basic ligand?
It is basic. Neutral.
Neutral.
Yeah.
So if you add palladium to the N-heterocyclic, if you mix the palladium acetate and N-heterocyclic carbene, the oxidation state of palladium is going to change or not?
It will be changed.
If I take palladium acetate and N-heterocyclic carbene, what is the oxidation state of palladium? It remains as it is, or it is going to change?
It is going to change.
Its palladium oxidation state is going to increase or decrease?
Increase.
Increase?
It will be decreased.
Decrease?
Zero. Yeah.
Huh.
2 to it
No,
will be decreased.
because
2 to
you
0.
told that it is a neutral ligand, so that it is not
Yes.
going to change at all. It is ineffective, right? Yeah, it is neutral ligand, right? It is
Yes.
neutral means it is not going to change its oxidation.
Yes.
That is the
It is.
advantage of N-heterocyclic carbene. So why PEPPSI ligands are required? Because so many N-heterocyclic carbenes are available in the literature, like imidazolium salts and like diisopropyl imidazolium salt on the both sides. What is the necessity of PEPPSI ligands?
When compared to other palladium NHC palladium NHC catalyst, palladium PEPPSI gave the best results. There are so many reports are available on palladium PEPPSI.
Is there any better selectivity compared to?
Yes, sir. Yeah. When compared to palladium NHC, it has better selectivity because it is attached with pyridines. So.
Okay. So I think you mentioned that it is not necessary to use that PBAP as a surfactant.
Yes, sir. In case of
Yes,
coupling reaction.
in
Yes.
some reactions. So
Yes.
actually, what is the role of PBAP in normal triphenyl phosphates and in the normal palladium NHC ligands? Normally, TBAP is used, but in the palladium PEPPSI ligands, TBAP is not required. So, what is your explanation? Why?
Normally, TBAP used as an ionic liquid, sir. It is used as phase transfer catalyst.
Okay.
But in my case, there is no need of TBAB, sir. Palladium PEPPSI itself acts as an ionic liquid and also catalyst.
Yes, in your case, it is not at all required. I understand that. But
Yes.
Normally in the palladium NHC ligand catalyzed reactions, TBAP
They use it as ionic liquid, sir. Phase transfer catalyst. They use it as ionic liquid.
okay, it is used as ionic
Usually,
liquid as a source of solvent.
Yes.
To get the high boiling means you can conduct the reactions at the high boiling
Yeah.
temperatures. Okay. Okay. So, what is the actual role of palladium here? Either palladium 2 is playing a role or palladium 4 is playing a role.
Palladium 2 is.
Palladium 2, palladium 4 complexes are not active for this reaction.
No, sir.
No.
Palladium 4 is not active.
Why? What is the reason?
I did not check it, sir, but according to my knowledge, I think so. Palladium 4 is. I did not tried with the Palladium 4, sir.
Okay. And palladium 0? What about palladium 0?
No, sir.
Because palladium triphenyl phosphine they have used, right?
Yes.
You told in the introduction just palladium triphenyl phosphines have been used for the Suzuki cross coupling reactions. Palladium tetrakis triphenyl phosphines and others. In that case, palladium. What is the oxidation state of palladium? It is
0.
Yes. So palladium 0 is also active. Palladium 2 is also active.
Also
Palladium
active,
4.
but I did not tried with Palladium 4, sir.
Okay. Okay, very nice. Did you try any asymmetric reactions?
No, sir. I did not tried it.
Yeah, it is very nice, and you have defended very good and also published in very good journals.
Thank you.
And my suggestion is better to go for the asymmetric version.
Okay, sir. I will try in future.
What is your future plan from this work?
I want to do PDF in
heterocyclic carbenes or in other direction?
Heterocyclic carbene.
Okay. So last question I would like to ask you whether these ligands are electron donating or electron withdrawing.
It depends on electronic properties, sir. Depends on substituents.
Yeah, so that is true. It is electron donating ligands or electron withdrawing ligands?
Electron donating.
Donating. So is there any possibility to make it as electron withdrawing?
I don't know, sir, exactly. I don't know exactly.
Because you mentioned in the introduction because of the sterically bulky and there are some properties which can make them electronically rich.
If Palladium PEPPSI has electron withdrawing substituents,
Okay.
then I don't know exactly, sir. Either it is withdrawing the electrons or donating electrons, but dropping is as observed, sir.
Okay, very nice.
Electron withdrawing nature.
Okay, better to try in the future if you get any opportunity on the asymmetric version of this Suzuki cross coupling reactions and also CH relations. It is a very nice piece of work and you have published in very good journals.
Thank you. Thank you.
It is really good. Okay, thank you.
Thank you.
And all the best.
Thank you. Thank you so much.
Now I request Professor K. Krishna Reddy sir, Dean Faculty of Sciences, please give your comments.
Thank you, Dr. Gingiridi. I am very much pleased to inform that one of the scholars from chemistry department, Anusha, made a nice presentation, and we are very much thankful to the external examiner, Professor KVS Ranganath Garu, for his interaction, and, asking the queries made by the other adjudicators also. For the information to Professor Ranganath Garu, we are having the 33 academic departments in Young Yogavemana University. Among these academic programs, the chemistry is the leading one. We are having the vibrant faculty. Among them, Dr. Vasugovardhan Reddy is also notably considerable scholar in the area of chemistry globally. And the student, Anusha, she tried hard and she worked with the limitations what we have in the budding university. And she made very good publications and also presentation. I wish her the best of luck, and hoping that she may continue due to the societal activity. In spite of that, she may continue for this work elsewhere on the globe if possibility comes. So I have one question to Mistress Anusha. What is your dream goal? మీ జీవితాశయం ఏమిటి?
As of now, I want to do PDFs. As
You
of
want?
now, I want to do PDF in USS.
Amma, dream goal is I want to do, I may do, I want to do, I wish to do, I can do, is not the dream goal. Dream goal is above all, is pertaining to you only, not for others. It is not a social bonding. It is not a social activity. It is not the humanospheric activity. It is the dream of yours. Please tell me now.
I want to become a good scientist, sir.
Excellent. I want to be God. Yes, I will do. I will make as I will want. I wish to be.
Okay.
Hoping that it will be become no problem. And I congratulate Dr. Vasugovardhan Reddy and also Srimati Anusha to declare that she is fit to get PhD after completing the formalities of our varsity. And now, formally, we can call you as a Dr. Anusha. Without hesitation, I am telling you, please. So, we congratulate Sir Ranganathan Garu. Please, you do congratulate her, sir.
Yes,
So,
yes. Very nice presentation. All the best. And congratulations to
Thank you very much.
Anusha and Srimati Anusha and also Vasugovardhan Reddy for successful completion of your PhD. It is a very nice piece of work.
Excellent, sir. Excellent for your nice, encouraging words. And really, I have to congratulate the Department of Chemistry for making a constructive Viva OC for about marathon Viva OC for 1 hour 10 minutes. And they made it very successfully. And I congratulate individual faculty and in general, in particular, Dr. Vasugovardhan Reddy and Dr. Anusha. Now I will hand over the mic to UOS Chairman, Dr. Chinnagengiridi.
Thank you very much. Now it is time for discussion. Any queries from the audience, faculty members? Any queries?
Unread. Okay.
So what's the difference between the all about palladium palladium and usual orbital palladium? That is different between what?
I did not get you. Can you?
Usually orbital palladium.
It is argon. Dating. It is dating bomb.
చూద్దాం చేతి అయితే హైలైట్ పెట్టాలి.
So finally, process one relation. Whenever this one relation compound.
Yes.
So we want to do other research. So if you know better the part that can lead to them, then they work better.
Okay.
So one more doubt is that usually when catalyzed reaction, we can see the formation of palladium complexes by
Yes.
catalytic process by oxidation addition. So have you observed anything for this one? Your substrate is migrating to other product, the Xps Spectra.
No.
So during the, in the final step, when after the formation of plasma, palladium, and so on, two ion groups can be used to combine together to give the
Product. Yes.
For example, in the other case, it may be other nuclear ion combined.
Yes.
Right?
Yeah.
So have you observed the migration of the substrate to the Xps group?
No, sir. I did not.
What is, I mean, why is that like happening? So is there any, I mean, the interior that is happening because is there any difference between the bond about the that would have been answered. If you know the bond between the palladium and iron, in your diagram the palladium,
Okay.
and palladium and this, then you can also get why it is not happening. The transfer of iron group goes to NHC. Since the transfer doesn't go to only use substrate. For example, in your Homo reaction. So during the process, you can see the process of diametric palladium. So as in the final step, it is supposed to combine both the substrate to give you the Homo product.
Yes.
For the identity.
Yes. Yes.
And during that point, why the array group is not transferring onto the individual part? Same side, both are very important for it.
Yes, sir. There is a possibility. After the reaction.
Why the array group is not transferring to the individual part?
Yes.
One difference between the engines with carbon and palladium with the the HP was point. So that's
Okay.
the solution. Can you please go to slide number 55? Yeah, yeah. Now, that will define right side is the left side the river.
Okay.
So that's not
Okay.
Can you go to slide 33?
80, sir.
Yeah. So how it happens? Have you observed the liberation of hydrogen?
Yes, sir. We have observed liberation of hydrogen.
I mean, what is making it to, I mean, the form of when oxidated.
Oxidation, yeah.
What is that? What is
8 as an accident, sir. We are using 8 as an accident.
without even have a testing?
No, sir.
Why so?
I have tested with oxygen balloon, sir, and I have tested in open air. I did not test in.
In that condition, you have been checked whether the oxygen is responsible for your oxidative process or not.
Because it is the oxidation, it required oxidant, sir. So that is why I did not observed in inert atmosphere, because it needed oxidant. Yeah, yeah, but, yes, I got it. Yes. Okay. Thank you. Thank you. Thank you. Thank you. Yeah, fine. Yes, sir. I know. I got you. I can understand. Yeah. It is. It is invented in no machine no. Yes, sir. Software. No, yes, sir. Bleaching of palladium is observing in recovered palladium PEPPSI. There is no palladium intention. Yes. So that is yes. Palladium chloride, sir. These are the, related to palladium chloride. 2, sir. Palladium 2. Plus 2. Palladium 2, sir. It has only one electron at the outer orbital. Sir. 2P leaching. Okay. Okay. Yeah. It, okay. Okay. Palladium leaching, after leaching, it will be converted into nanoparticles. Like that. It's like it is like a ligand, sir. Ligand. What is a ligand usually, sir? Usually. What is the suitable base and ligand for homocoupling reaction of bromoaromatics? In generally, most of the homocoupling reactions of bromoaromatics are used as ligand, that is triphenyl phosphine, ionic liquid, and tertiary butyl ammonium iodide, and tetrabutyl ammonium bromide, and carbenes are used as a ligand for homocoupling of bromoaromatics. Do you know any catalyst which can give homocoupling product of aromatic boronic acid? As per my literature knowledge, palladium acetate, palladium triphenyl phosphine, palladium chloride catalysts are used for the homocoupling of aromatic boronic acid, and also copper based catalysts are also used for homocoupling of aromatic boronic acids. In chapter 12, page number 33 table, I have corrected as fibromo. Yes. Fibromo, structure of fibromo to aminopyridines. Structure. Not name, sir. Structure. It is not in. There is no mistake in slides, sir. It is mistake in these. Okay. Okay. Sir. I hope palladium PEPPSI catalyst is soluble in organic solvent. How did you recycle your catalyst? Is your catalyst act as a heterogeneous? Palladium PEPPSI is a homogeneous catalyst. It is soluble in organic solvent. After the complete conversion of starting materials into product, the reaction mixture was pulled to 25 degrees and distilled off the solvent by using rotoevaporator. Later extracted with the water ethyl acetate and purified through column chromatography. Okay. Yes. What is the significance of semidax of your catalyst? Semidax spectroscopy experiments were performed for recovered palladium PEPPSI complexes and observed decrease in palladium content from 9.27 to 0.449. For this purpose, use semidax spectroscopy. How Xps semidax? How XPS technique does help in getting better yields in catalytic reaction? What is it? What is its important to know the binding energy of every catalyst? We were comparing the XPS technique of freshly prepared and recovered catalyst after fifth cycle in XPS spectroscopy survey, reported recovered catalyst and observed the lowering the peak intensity of palladium and chlorine. We observed palladium intensity of palladium is decreased. Freshly prepared and recovered catalyst. What is the nature of NHC ligand? Is it donating, accepting, or neutral? NHCs are electron-rich, neutral, sigma donor ligand. It depends on the substance and that. Potassium distributor. No, sir, I did not mention anything. But in case of C2 or benzoxazole, in case of benzoxazole, sir, I have used sodium tertiary butadiene. Yes. 45. Cesium carbonate is less. Yes, sir. Yes. But in compared to cesium carbonate, it is less expensive. Yes. Yes. And also get 91% yields when compared to 89. It is a better yield. Yes. More other. Yeah. Due to steric inherence, it shows as sir, these are the orthosubstituted methyl protons. These methyl protons, A methyl proton. 24, yes. Here we are using aryl chlorides and instead of aryl chlorates. But we are changing the moieties, reacting moieties. Benzoxazole we are using and also changing the aryl chloride. Yes, sir. Yes, yes. But when compared to price size, it is better. Up to 150, sir. I think. Yeah. I did not observe after 150 degrees centigrade. Up to I have checked up to 150 degrees centigrade. Yes, sir. Stable. I have recycled catalyst through column chromatography. Yes, sir. Yeah. Yes, yes, yes. Yes. Uh, sir, no, somewhat decrease. Yes, yes. I have added some more. Yes. I have calculated according to the Palladium PEPPSI compound. If I get yes, yes, yes. Okay, okay. Yes. It both bleaching of palladium and also decreasing quantity also. Bleaching of palladium. Yes. 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 Bleaching of palladium is yes. Catalyst loading. I did not sorry about that. When you decrease the loading of catalyst, it will be. M+3 like that.
Now I request Professor KVS Rangana sir, please conclude.
So, yeah, thank you for your comments and based on the reviewer comments and on my behalf of my own comments, Mrs. Anusha has successfully defended PhD for the queries given by the referees and audience, and it will be uh, given and honored with a PhD degree to Mrs. Anusha without any hesitation after completion of all formalities. And I would like to congratulate her for her successful defense of PhD thesis. And I wish her all the best for the future. Yes.
Thank you very much.
Ranganath, thank you.
Yeah, sir. Thank you for giving me this opportunity.
Thank you, Ranganath. So once again, thank you for all audience, especially chemistry department, other faculty members, and students. Once again, thank you, one and all. Thank you.
Thank you, sir. Thank you.
Okay, go.